Okay, welcome to Introduction to Photonics. In one of the previous lectures, we considered the response of a medium to an electromagnetic wave. In this case, we are talking about a light wave, and we were characterizing that as a mass spring sort of model, and we were tracking the resonances that appear because of this. We basically said that the response epsilon, which is characterized through the epsilon, is typically complex in nature, right. So, it's got both real and imaginary parts, and it's also frequency dependent. Okay, so those are two properties that we looked at. Now, in today's lecture, we will consider a case where your excitation is so high that your response is not linear anymore. Okay. So, what happens if you work in a regime in which your excitation, in this case let us say in the mass spring model, it is like the excitation corresponds to pulling that mass, stretching that spring. You stretch it to such a large extent that the displacement is not, is not changing linearly with respect to the excitation. Okay. So, what happens in that case? Nonlinear response of materials to light. Okay. So far we have characterized the response of a material to light through the displacement vector, which said is dependent on the electric field applied to that material, and the specific thing that is changing is your epsilon r, that is what is defining the response of the medium, and that we said is equal to 1 plus chi, where chi is the susceptibility of the medium. So, we wrote this as epsilon E plus epsilon chi multiplied by E, and this term we call the polarization response of the medium. Okay, so that is actually representing the polarizability of the medium, and that is not to be confused with the definition of polarization, light polarization, which is essentially how E, the terminus of E changes as it propagates. Okay, so this is actually a slightly different thing that we are talking about. This is talking about polarizability of the medium. But nevertheless, if you plot the magnitude of P with respect to the magnitude of E, according to this expression, you would say that you should get just a linear response like that, right. In reality, what happens is it is linear, but only up to a certain level of electric field. Okay. So, beyond a certain electric field values, it starts deviating from that linearity. So, it has a nonlinear response it exhibits a nonlinear response beyond a certain value of E. Okay. So, most of the applications, including the communication applications that we consider in optical fibers, we typically rely on the linear response of the medium, and what we are saying is that linear response is valid, the approximation of linear response is valid only up to a certain electric field. So, what you really have to look at is when we are talking about the polarization, let me just drop the vector notation because we are just interested in the magnitudes. So, you have epsilon naught multiplied by chi e, that is the first order effect. But then you could have higher order terms, chi 2 e square plus chi 3 e cube and so on, right. Now, let us examine these higher order terms a little more closely. Okay, so, what does this higher order term mean? For example, what does this mean? It says that this response is proportional to E square, right. So, that is essentially saying you can have two different electric fields interacting with each other, okay, to provide a net response. So, going back to the mass spring model, we said the displacement is because of an applied electric field, right. That applied electric field, we were, what was that corresponding to when we were discussing that? That electric field was corresponding to the electromagnetic wave that was traveling through that material, right. That was the excitation that we were considering there. But now we are saying that if you have another field, okay, you could get a mixed response. You could have two fields mixing through this chi 2 term, okay. And similarly, if you are talking about the chi 3 term, which is called the third order susceptibility. So, chi 2 is called the second order susceptibility, and chi 3 related effects is called the third order susceptibility. There you could have mixture of three different electric fields, okay. And quite interestingly, these electric fields need not be at the same frequency. You could have one field at one frequency and another field at another frequency. Both are exciting the same location, both are exciting the same mass spring model. So, what do you expect the response is going to be like? It will be a mixture of both those frequencies, right. So, now when you invoke these second order and third order terms, now we are starting to talk about mixing frequencies, mixing multiple frequencies. So, just to give you an idea, if we talk about second order susceptibilities, now I can come in with E1 e power j omega 1 t and then E2 e power j omega 2 d, right. And then I can go out if this medium has certain value of chi2, then you can go out with multiple terms because it's omega 1 and omega 2 beating with each other, right. So, you could have let us say 2 photons at omega 1, they could get mixed with each other, and so you could actually get 2 omega 1 as one result. You could have omega 1 plus omega 2 as a result. You can have omega 1 minus omega 2 as a result, or you could have 2 omega 2 as a result. Okay. So, interesting things happen. You are generating new colors, okay, once you have this medium which exhibits chi2, and of course, the value of chi2 is very small, right. So, it's in the order of let's say picometer per volt, okay. So, because chi2 and then it's interacting with the electric field, so that's why we are talking about picometer per volt. So, it's a fairly small number. So, you would say that to really see the effect of something like this, you need to go to several orders of magnitude volt per meter, right. So, you need to have very high electric fields to see this sort of effect, but nevertheless there is a possibility now that you can mix frequencies, you can generate new frequencies, okay. So, where do you see 2 omega 1 or 2 omega 2 becoming useful? That is actually what we call as second harmonic generation, right. So, clearly 2 omega 1 corresponds to the second harmonic of omega 1. So, you have second harmonic generation. So, twice the frequency, what would that mean in wavelength? Half the wavelength. So, now you have the possibility of converting a laser, let us say with 1 micron wavelength, right, that is going through this medium, you can actually have half a micron come out of that, okay. How it happens and all of that, we'll go into details later on, but that's what is possible through this medium. 2 photons, 2 electric fields at omega 1, they beat with each other and they create second harmonic generation. And that's what you have in your laser pointer. That's why I was asking about the laser pointer a few minutes ago. So, if you look at a green laser pointer, so what exactly do you have? That green laser pointer has got neodymium YAG crystal. YAG is yttrium aluminum garnet, that's actually a glass crystal. So, neodymium is doped in that crystal, and just like ytterbium, neodymium has a transition at 1064 nanometers, okay. So, you could make a 1064 nanometer laser out of a neodymium crystal if you can pump it with some radiation around 810 nanometers, okay. So, in that laser pointer you have a 810 nanometer laser that is actually pumping a neodymium YAG crystal which has got mirror coatings on either end. So, you can actually make a laser out of that. So, that laser is happening at 1064 nanometers, and that output is made to pass through a crystal, right. KTP is one crystal potassium. What does KTP stand for? Does not matter. So, there are crystals which have a large value of Chi2. So, you send it through one of those crystals, then you can get from 1064 you can get 532 nanometers, and that is the green laser that you see from a green laser pointer. It is not like a green semiconductor laser that is emitting that. Okay, that is actually, you know, it is a very good example for second harmonic generation. And you could also do some frequency generation, and more importantly difference frequency generation. I say more importantly different frequency generation because normally it is very difficult to achieve lasers in that work in mid-infrared region, mid-infrared and far-infrared region. Okay. One of the reasons is when you look at the energy corresponding to those long wavelength region, you find that the energy is very small with respect to what it's comparable to thermal energy. So, when you have when you want to generate light corresponding to, you know, closer to thermal energy, you look at your Boltzmann distribution, it tells that it is very hard to maintain an inversion so that you can emit light with very low energy. Okay. So, in those sort of cases, if you want mid-infrared radiation, this is actually a very good way of producing that, because you just come up with two lasers with the right spacing, you can actually achieve, you can generate photons at a much longer wavelength corresponding to the difference between the two frequencies. Okay. So a lot of interesting things can happen through second order susceptibility. I will come back and talk about third order susceptibility also, but we'll stay with this second order susceptibility and see what else can be done with that. Any questions up to this point? Okay. One of the other things that is possible with due to Chi2 is called the Pockels effect. So, what is Pockels effect? When you have a material that exhibits a large Chi2, this sort of phenomena is possible. You could put an electrode across that material, okay, connect this to some voltage source, right. So, you have a electric field across that material, and through that electric field you can control the response of the medium. Remember when we talked about that mass spring model, we said that material, in that case the electronic response, is to an applied electric field. We did not at that point quantify or qualify what that electric field source is. It could actually be an external electric field source, right. So, even that can change the response of the medium, okay. So much so that if you are looking at light that is propagating through that medium, that light actually sees a different refractive index. Okay. That refractive index, which we can call as N of E, is given by N naught, which is the refractive index that it has originally, minus 1/2 of R N naught cube multiplied by E. Okay, where N naught corresponds to the refractive index of the medium, E is the field applied across the medium, and R is known as the electro-optic coefficient. That electro-optic coefficient is a slightly different form of chi2. So, R is actually proportional to chi2, the second order susceptibility. So, what we are saying here is through the second order susceptibility and an applied electric field, you can change the response of the medium, so such that the refractive index that this light wave sees as it propagates through the medium is changed. Okay. To give you an idea for this electro-optic coefficient for lithium niobate, which is one of the very popular crystals, lithium niobate has R of 30 picometer per volt, right. You can see where that picometer per volt unit comes from. So, that multiplied by electric field, which is volt per meter, is going to give you a dimensionless quantity, right. So R for lithium niobate is 30 picometer per volt. For silica, that R is very low, it is 0.01 picometer per volt. Okay, it is negligible. So, you can say that chi2 for silica is negligible. And if you look closely as why chi2 is negligible for silica, it so happens that all centrosymmetric material, right, all centrosymmetric material have a very low chi2, and that also means that if you are silica, which is highly amorphous, if you are talking about fused silica, that's amorphous, that amorphous material has a high level of centrosymmetry. We won't go into the details of what that means. I mean, it's basically a crystallographic notation. But lithium niobate, which is actually a crystal, does not have that centrosymmetry, and that can exhibit a large electro-optic coefficient. In fact, part of my PhD research was on this. Can we break the centrosymmetry of silica so that we can get a increased electro-optic coefficient? And I should say we were successful in doing that, and we were able to enhance the electro-optic coefficient, but I won't bore you with those details right now. The point is, if you have a large electro-optic coefficient, if you have a large chi2 essentially, you can actually create a large change in the refractive index of the medium through an applied electric field. Okay. So, why is that important? Because if you change the electric field, what else changes? The phase of light that goes through this medium, that changes. So, the phase is given by, you have some phi naught minus 2 pi over lambda, the refractive index, which is the refractive index change is given by 1/2 of R N naught cube E multiplied by the propagation length. So, in this case, let us say the propagation length is given by L, so multiplied by L, right. So, what we are saying is that the phase of light can be manipulated using an external electric field. So, if you can manipulate the phase of light, what is possible? You can, interfere this light wave with another light wave, or let us say you take a light wave, you split it into two, okay, one part goes through this phase modulator, the other part goes without actually accumulating much phase, and then you mix them together. Then the relative phase difference determines whether you have constructive interference or destructive interference, right. And that relative phase difference now is controlled by this external voltage. Do you see where I am getting to? So, let us say you have a structure like this. You manage to split the light two ways, one part going this way, one part going that way, and on this part you have incorporated two electrodes, right, and you have a field applied, electric field applied across that, okay, and these two come together over here and interfere, and you go out, okay. Now, what are we saying is, by applying this electric field, I decide whether I get constructive or destructive interference over here. I can make light appear over here, or I can kill that light. So, I can do an intensity modulation with this, right, an voltage controlled intensity modulation. So, if I want to communicate data, I have my data, I am speaking now, and let us say this is actually transmitted live somewhere. You are digitizing the voice, you are digitizing the video, you communicate that as data. That data is available as a voltage. Now, you want to send this over a long distance. So, you are going to send this, you are going to try to put this onto an optical signal and send it through an optical fiber communication system, right. So, you need some device which can convert this voltage changes into changes in the intensity of light. That will be this sort of a device, okay. So, essentially what we have here is a phase modulator. So, this section corresponds to a phase modulator, but since that phase modulator is within the structure, which is like a Mach-Zhender configuration, right, Mach-Zhender interferometer configuration, because of it's in the structure, this phase modulation is converted to intensity modulation. You are essentially gating light all through this V of t that you are applying to this electrode, and that is provided this waveguide is actually made with this material which has a high electro-optic coefficient. So, if this entire structure is made of lithium niobate, right, then I can actually have this phase modulation, and through the phase modulation you can do intensity modulation. Okay. Any question about this? Sorry, both the arms? Not necessarily. So, the question is whether both the arms has to be made out of lithium niobate. Not necessarily, it could be some other material, right, but it is easy to make it in lithium niobate because you can just define all those waveguides in one material. If you have to do it on some other material, let us say glass, right. So, you have to have a glass waveguide everywhere else, and then corresponding to the phase modulation region, you need to take lithium niobate and stick it in there and make sure it is all aligned and integrated and all that, which is a very tough thing to do. Okay. So, you might as well just define the entire structure in lithium niobate. So, R is proportional to chi, the proportionality factor is some 3 pi by 2 or something like that. It is just directly proportional to chi 2. R is proportional to, so we are saying R is proportional to chi 2. Okay. So, so let's go into the details. Let's actually say this part, let's call this delta, well, delta phi of E. Okay. So, let's figure out the voltage at which you can get delta phi of pi. Why is that important? Pi, because pi phase difference can mean that you are going from constructive to destructive interference. So, I am turning the light on to off. Okay. So, let us quantify that voltage. So, what we want is del phi of E to be pi, and del phi of E is given by 2 pi over lambda multiplied by 1/2 of R N0 cube. This particular voltage that gives me pi phase shift, I will call that V pi. So, that electric field is V over D. What is D? D is the thickness of this material. So, that is the D is the distance between the electrodes, multiplied by L. Okay. So, you can rearrange terms, of course, you can cancel this, you can cancel pi over here, and if you rearrange terms, what you get is an expression for V pi. V pi is going to be given by lambda multiplied by D divided by R N0 cube multiplied by L. Okay. So, let us see if it makes sense. So, V pi is smaller when D is smaller. Makes sense, right? Because for the same voltage, if D is smaller, that corresponds to a higher electric field, right? Higher the electric field, that means more the modulation, so more the phase change. Okay. V pi is inversely proportional to R. So, again that makes sense because R is representative chi 2. So, larger R, larger the electro-optic coefficient, more the phase change for a given electric field, right. And it is also inversely proportional to L because phase is accumulating over distance. So, longer length of that interaction region, more will be the phase change, right. So, let us actually throw in some realistic numbers to this. So, let us say we need V pi equal to 5 volt. Why do you want V pi equal to 5 volt? 5 volt corresponds to TTL. Okay. Now, of course, V pi, if you want it to be compatible to CMOS logic, you would say 3.3 volt. You want a relatively small number through which you can control this amplitude modulator. Okay. So, let us pick V pi equal to 5 volt. We know that for lithium niobate N0 equal to 2.2 and R for a particular configuration of electrodes, it is given by 30 picometer per volt. Let us say lambda we are working at 1.5 microns. What else is left? D. Let us say the D is 10 microns. The separation between the electrodes is 10 microns. So, question is what value of length is required so that you can get a V pi of 5 volts, right. So, this would imply that length is given by lambda multiplied by D, which is 1.5 into 10 power minus 6 multiplied by 10 by 10 power minus 6 divided by R, which is 30 multiplied by 10 power minus 12, N0 cube 2.2 the whole cube multiplied by V pi, which is 5, right. And right off you can see 10 power minus 6, 10 power minus 6 and 10 power minus 12. So, those cancel and 10 goes into 3 as 30 and 1.5 multiplied by 10 is 15, goes in 30 as 2. So, it is 1 over 10 into 2.2 the whole cube. 2.2 the whole cube is roughly about 10, right. If somebody has a calculator, you can check that. So, what is the final value you get? It is roughly about 1 centimeter, 9.89 millimeter, right. So, that is roughly 1 centimeter. Okay. So, with just 1 centimeter of lithium niobate, right, provided you have a 10 micron separation between electrodes, you can achieve a V pi of 5 volts. Okay. So, you can make a reasonable modulator with this. Now, so this is in terms of so, if I have this expression for V pi, I can actually plug that into this expression over here. So, I can tell that phi of E in terms of V pi is going to correspond to phi naught minus pi into V of t divided by V pi. Because V pi is given by this expression and E is nothing but V over D. So, that is where you can see that in the denominator is lambda D, R, N0 cube, L is all there. So, you can put it up like this. And the other thing that you get to see is when you are looking at the output intensity, right, let us call it I out over here. Let us say what is coming in is I naught, and you manage to send I naught over 2 there, I naught over 2 here, and then it is going through a relative phase change. So, I naught can be I out, you will find that if you do the math, it will be like I naught over 2 multiplied by 1 plus cos of delta phi, or you can just write it as I naught cos square delta phi by 2. Delta phi essentially is the phase difference introduced by the phase modulator. Okay. So, if you plot I out as a function of delta phi, that is basically saying it is a cos square function. So, it is going to be something like this. So, so when delta phi equal to 0, that is going to be the maximum and that corresponds to I naught, and then when delta phi equals to pi, right, cos square pi by 2 is 0. So, you go to 0, and then when it is 2 pi you go to a maximum, and then 3 pi you come back to 0, and so on, right. So, key thing is that this delta phi is a function of the voltage that is applied, right. So, by changing the voltage you can actually change the output of that modulator. So, you can make the output go from maximum to minimum, and the corresponding voltage here is what we are calling as V pi. So, the voltage corresponding to maximum to minimum is what we are calling as V pi. Okay. So, if you have something like this, then what you can afford to do is you can afford to bias it. For a cos square function, the best place to bias it would be at quadrature. So, it is pi by 2. So, if you have a bias phase bias of pi by 2 between the two arms, then if you have some voltage waveform like this, you see a corresponding intensity waveform at the output. Okay. So, you can essentially imprint your modulation which is in voltage. So, this is basically V of t, and correspondingly you have an output intensity which is changing with respect to time. Okay. So, you can this is what we call as intensity modulation using this Pockels effect. Okay. Any questions about this? So, this is voltage controlled phase modulation. Voltage control phase modulation, which when we incorporate into a Mach-Zhender configuration, you have a voltage controlled intensity modulation. Okay. Now, of course, there are applications like in modern day communications, you play around with the phase. You're not turning light on and off anymore. You are actually trying to encode the information in phase going from 0 to pi or 0 to pi by 2 or whatever, right. So, if you are interested in phase modulation, you can just use the lithium niobate modulator as it is. You do not need to put it inside a Mach-Zhender interferometer. Okay. So, you can achieve direct phase modulation. So, this is what you are going to be doing yourself in this week's laboratory session. You will be given a lithium niobate modulator. So, you will actually connect it up and apply an external voltage. You apply a DC voltage and you connect the lithium niobate modulator to a light source and the other side to a detector, and then you, for applied DC voltage, you will see whether the power that is detected, whether it is going through this curve, this cos square curve, and once you have verified that, then you will apply a bias, appropriate bias to your modulator, and so that it comes to that that part where you have a linear in this point you have a sort of a linear response. So you bias at the center of that and then you apply some voltage modulation, then you can see the corresponding change in the intensity at the output. Okay, so you will send it to a photodiode and then take the output of the photoreceiver to an oscilloscope to see whatever waveform that you sent in as voltage to that lithium niobate modulator is the same waveform that you are seeing in terms of intensity as well. Okay. So, what happens if you bias at this point? If you bias at that null point and you apply some voltage there, voltage swing there, what do you expect to see? So, that basically says your DC is 0, but you have a modulation. So, corresponding to that voltage you will have light go through, right, you are letting. So, if you do this, so let's actually put the modulation point somewhere over here, right, and if you do this, what do you expect to see at the output? So, corresponding to the this 0 over here in terms of voltage, you have 0 intensity, but when the voltage goes to the positive cycle, what do you get to see? There will be a corresponding positive cycle, and then it goes to a negative cycle, you still are letting light through. So, you are actually having, for the negative cycle also you have. So, you essentially have twice the modulation frequency. So, if your frequency of modulation is FM over here, you get 2 FM over here, right, and that is over a bias of with 0 intensity. So, that is actually what you call as carrier suppressed modulation, because your carrier is essentially the light carrier is at a null point. Okay. So, what you get here is carrier suppressed modulation. Okay. So, you have your modulation terms sidebands, but your carrier is suppressed in this case. Okay. So, let me stop at this point. And of course, we can look at other examples as in second harmonic generation, difference frequency generation and all of that. I will desist from doing that. All I can say there is this picture is valid. So, you can go in with photons at 2 different frequencies. If you go through a Chi2 material, you can get all these other components. Difference between the 2 frequencies, you can get double the frequencies and so on, right. So, you can achieve frequency conversion through a nonlinear medium. Okay. And in this case, what we are saying is we are modulating the phase of light through this Pockels effect, through this external. In this case, we said this could be interaction between 2 electric fields. One electric field in this case is the applied electric field, and the other electric field is the one that is going through the material corresponding to the light wave. Okay. So, that is the interaction that we are seeing here, electrically controlled phase modulation. Okay. So, let us stop here, and tomorrow what I would like to do is to jump on to the third order effects, third order susceptibility effects, what can be done with those sort of material that exhibits a large Chi3.